Alright, lesson 3 is over acceleration. Acceleration is a measure of the change in velocity during a period of time. Average acceleration is a change in velocity during a time interval divided by the time interval during which the velocity changes. That's a really wordy definition, and we'll have an example of it in the slideshow. Acceleration, or changes in velocity. An object accelerates when its velocity changes as a result of increasing speed, decreasing speed, or change in direction. Remember, those are the three things that can change velocity, and a change in velocity is acceleration. Roller coasters are a great example of change in velocity. Whenever you change speed or direction in a roller coaster, up, down, spinning around, slowing down as you're going up, going faster as you're going down a big drop, all those things are changes or are acceleration because they're changes in velocity. Acceleration can occur when you're slowing down. This is the difference between a science definition and what we normally talk about right here. Our science definition is any change in velocity is going to be defined as acceleration. We like to think of in normal everyday life as acceleration just meaning speeding up, but we need to work past that. We represent acceleration with arrows like velocity. The larger the arrow, the greater the acceleration. Alright, so positive and negative acceleration. Positive acceleration, we say that in our first example right here, we say that the car is accelerating because the velocity is increasing. In our second example, we say that the car is accelerating because it's changing in direction, which means that the velocity is changing even though the speed is constant. And negative acceleration, we say that the car is accelerating because the velocity is decreasing. Decreasing velocity is still acceleration, although it's negative acceleration. So, calculating acceleration. If an object moves in only one direction, you can calculate its average acceleration using this equation. A is equal to v sub f minus v sub I divided by t. And when I say v sub f, I'm talking about it should look like v, and then we have another one that's a little f below it, or a little t below it. So you have to stick with me here while I'm writing that out. So v sub s will look like that when you normally see it, and that'll be the same for v sub I. The sub is just subscript below the actual writing. So A is acceleration, v sub f is equal to velocity final, v sub I is equal to velocity initial, and t is equal to time. Average acceleration is measured in meters per second squared, and I talked about this per second squared thing earlier in the year. When we start to cancel our units out, you'll see that we have 2-second values on the bottom of our train tracks. Alright, so calculating acceleration practice. A bicyclist started from rest along a straight path. After 2 seconds, his speed was 2 meters per second. After 5 seconds, his speed was 8 meters per second. What was his average acceleration during the time 2 seconds to 5 seconds? So, first thing you need to do is list what you know. We know that our initial velocity was 2 meters per second. We know that our final velocity was 8 meters per second. And our time, we're saying from the time 2 seconds to 5 seconds, so 5 minus 2 gives us 3 seconds. So our time is going to be equal to 3 seconds. What are we looking for? In this case, we're looking for acceleration. So we use our formula. A is equal to v sub f minus v sub I divided by t. You can plug in all your values. A is equal to 8 minus 2. Again, 8 is coming from up here. This is where we're getting 8 from. That's our final velocity, right? We're plugging 8 in for v sub f, and that goes right there. We're doing the same with 2. V sub I is 2 meters per second. Plugging that in. And finally we have our time is equal to 3 seconds. So in your calculator you would do 8 minus 2 and then divide that by 3. Make sure you punch the top part in before you divide. That will give you 2 meters per second. Because again, if we have seconds here, so we're going to have seconds on the bottom, that's going to give us 3 seconds, and those will cancel out. And we'll go through some examples on the board that will make that a little easier to see and understand. Alright, so a speed and time graph. Speed is on the y-axis, time is on the x-axis. Always, if time is available, time is almost always going to be on the x-axis. So that's the one that runs left to right, not up and down. An object at rest will have no y value because it's not moving. I'm going to be jumping back and forth between two different slides here. So an object at rest will have no y value because it's not moving. So that's saying that an object at rest is going to be at 0, and it's going to stay at, imagine my line being straight there, stay at 0 all the way across. The reason for that is, if it's not moving, it's not accelerating, so there's no reason for us to say that's going up and down on our y-axis here. But time's still passing, so it's going straight across. Again, remember that that's supposed to be a straight line. An object with constant speed will be a straight line with no change in the y value because the speed is not changing. So, let's say that our speed is 30 meters per second, but it's a constant speed, so we're going straight across. So for 10 seconds, we're going 30 meters per second. Again, that should be a straight line, but so we have to realize that speed's not changing, so this should be straight across. We're not going to be going up and down on the y-axis. An object that is speeding up will be a straight diagonal line as speed increases and time elapses. So as speed increases, we're going to be going up. As time elapses, we're going to be going to the right. So we will have something that looks like that, going across. Let's label those real quick. This was our number 1. This is our second one. And this is our third example. So this was our 1. Ooh. I'll delete that out of there. So this is our 1. This is our 2. This is our 3. And we'll do our fourth one. An object that is slowing down will be a straight diagonal line as speed decreases and time elapses. So if we start at 50 meters per second, as speed decreases, we'll be moving down the y-axis. As time elapses, we'll be moving to the right of the x-axis. So we'll be going this direction. And we'll label that number 4. So hopefully that makes sense. Again, we'll see some more examples of this as we go through and do some practice work. That should do it for this slideshow.